Hello everyone. So today we are going to discuss about protection and deprotection of alcohol functional group. Protection, and we will also look at deprotection of alcohols. Okay, so what is the alcohol functional group? So in an organic molecule, when a carbon is attached to hydroxyl group, this R is representing a carbon atom. So when it is attached to a OH group or a hydroxyl group, this is what we call a alcohol functional group. Now alcohols can be of three types. We have 1 degree alcohol, 2 degree and a 3 degree. In a 1 degree alcohol, you will have oxygen bonded to carbon which has two hydrogens attached to it. The best example is ethyl alcohol. Here this oxygen is bonded to carbon which has two hydrogens attached to it. In a 2 degree alcohol, you will have oxygen bonded to carbon which has one hydrogen attached to it. This can be written as this molecule. This is an isopropanol, a 2 degree alcohol where oxygen is bonded to carbon which has one hydrogen sitting on it. In a 3 degree alcohol, you will have oxygen bonded to carbon which has no hydrogen or zero hydrogens attached to it. This can be written as this molecule. So this is a 3 degree alcohol simply because this oxygen is bonded to a carbon which has no hydrogens attached to it. This 3 representing a methyl group. Okay. So why we need to protect alcohol? So the first reason is why we need to protect alcohol is because under basic condition, this hydrogen of alcohol group can get deprotonated. And the second reason is the oxygen lone pairs present in alcohol functional group can react with any electrophile. Okay, this lone pair can act as a nucleophile and can react with electrophile. So to block this reaction, we also need to protect alcohol functional group. So these are the two reasons why we protect alcohol group. Okay. I also want you to know, suppose you are doing a reaction which has a alcohol functional group. So this is something interesting. Suppose you are doing a reaction where you want to cleave this particular bond. So what is the order of reactivity for the alcohol? So 1 degree will be more reactive than 2 degree followed by 3 degree. And if you want to break this bond in a particular reaction for alcohol functional group, the reactivity order for the alcohols is going to be the reverse. 3 degree will be more reactive than 2 degree followed by 1 degree. So this is basic intro about alcohol functional group. Now let's move forward and study protection and deprotection of alcohol functional group. Okay, so the first one we have is what we call the alkyl ether protection. Okay, we have alkyl ether protection. So what it is? So this is my alcohol functional group. When I react it with any haloalkane in presence of a base, so what is the reaction? So this oxygen lone pair will attack at this R group, will eliminate this halide anion, and this will simply generate an ether bond, and you have protected your alcohol functional group. So this is what we call alkyl ether protection strategy for alcohols. And what is the deprotection? How can you get back your alcohol group? So two reagents you can use. You can use trimethyl silyl iodide in DCM. You also need little bit acidic environment, or you can use BBr3 in DCM. So use any one of these particular reagents and you will be able to convert your ether linkage back to alcohol functional group. So this is deprotection and this is protection. Let me give one more reaction. Suppose I have a methanol and I am reacting methanol with methyl iodide. in presence of silver oxide in DMF as a solvent. So this is a protection. We are protecting alcohol group by forming an ether linkage, and this will generate this molecule. And what is the byproduct? Byproduct is going to be silver iodide, which will precipitate out in your reaction. So this oxygen lone pair attack this carbon, iodine is going to leave, and you will simply form the protected product. And if you want to deprotect and get back your methanol, either use trimethyl iodide or BBr3 and you will get back the deprotected product. Okay, let's talk about tertiary butyl ether protection. Okay, so suppose I have alcohol and I want to convert this molecule. Basically, I want to protect my alcohol by using a tertiary butyl ether protection. That's why it is named as tertiary butyl ether protection. So what reagent should I use? So you can use any of this, like you can use tertiary butanol under acidic environment, or you can use this particular alkene under acidic environment, or you can use this particular haloalkane under Lewis acid condition. Okay, so these are few of the reagents you can use. You can also use this primary amine with nitrous acid. So use any of these and you will be able to form this tertiary butyl ether protection. Now what is the mechanism? So all these molecules, all these reagents will generate this particular carbocation. Okay, this particular carbocation. How does it happen? So the tertiary butanol, so this is my tertiary butanol. I'm talking about the first one. So tertiary butanol under acidic media will generate, by eliminating water, it will generate this particular carbocation. Okay, later this water molecule will leave and it will form this carbocation. Similarly, if I take this alkene, the second reagent, under acidic media, this double bond will grab this proton and it will generate the same carbocation. Similarly, if I use this haloalkane in presence of Lewis acid AlCl3, the similar product I am going to get, and the byproduct is AlCl4 minus. Okay, and what about this nitrous acid? So when you have primary amine in presence of nitrous acid, first this NH2 will be converted into N2 plus, which will leave out as a gas, and you will once again generate a carbocation. So the byproduct here is a N2 gas. So in all of these reactions you are generating this tertiary carbocation. Okay, what happens next is, whatever alcohol you are taking, that will come, the oxygen lone pairs will form a bond with this carbon and will simply generate the product we are looking for. So this is how you can do the tertiary butyl ether protection, by using any of these reagents, and this is the mechanism. You generate a very stable tertiary carbocation which will be later attacked by the lone pairs of oxygen. So this is about protection of tertiary butyl ether. Now let's talk about the deprotection of tertiary butyl ether group. Okay, so this is my tertiary butyl ether protected group. Now about deprotection, if you want to convert this back into alcohol, you have to use a acidic environment. You can use trifluoroacetic acid, or maybe you can use HCl. So what is the mechanism? So this is my tertiary butyl ether group. Suppose I am reacting this with a HCl. So this oxygen lone pair will grab this proton, will eliminate chloride anion, and it will form the oxygen bearing positive charge. Now this bond is going to break. You will generate the product, and the byproduct is this very stable tertiary carbocation. So that's why this bond cleaves and it forms carbocation, because the intermediate is very stable. And furthermore, whatever Cl- has just left will come back and will form a bond with this carbocation, and the byproduct will be this molecule. So you need to know that, and this mechanism is following by SN1 mechanism, simply because we are forming carbocation and then the nucleophile is attacking. Okay, so you need to remember that tertiary butyl ether can be deprotected under acidic environment, and this is the mechanism. Okay, now let's talk about the benzyl ether. Benzyl ether protection. So you know the ether linkage is what we call ROR. Okay, and the benzyl group is CH2PH. So the reaction is going to be, we have this alcohol. In first step, we use sodium hydride as a base in presence of THF solvent, and in second reaction we are using benzyl bromide, and you are generating the product, that is benzyl ether protected alcohol group. Now what is the mechanism? So this is my alcohol. Sodium hydride is a very strong base, so H- will grab this proton, hydrogen gas is going to liberate, and you will generate a alkoxy anion. Now this will react with my benzyl bromide. This oxygen lone pair will attack at this carbon, bromine is going to leave, and you will form the product. So this is the mechanism. Now what about the deprotection? Suppose I want to get back my alcohol group. So which reagent should I use? So there are three reagents you can use. You can use hydrogen palladium supported carbon in ethanol, or you can use ranitidine in ethanol, or you can use sodium ammonia in ethanol. So if you want to convert your benzyl ether protected alcohol back into alcohol, you can use any one of these three reagents, and you will be able to get back your alcohol functional group. And if you use the hydrogen palladium carbon ethanol, the byproduct is a toluene. And we have discussed this particular mechanism in my one of the video where I talked about protection and deprotection of amines. Okay, so this is the deprotection and this is the protection of benzyl ether. Okay, I have found one very interesting question. So the starting material is okay, this is my starting material. This can be written as Cl3 C double bond NH OBN. Okay, so this CCl3 is here. This carbon is this carbon. This is double bond NH, double bond NH. This is my oxygen, and this CH2PH can be written as benzyl group. Now, what happens under acidic condition? Okay, Suppose I am giving a acidic environment to this particular molecule. So what happens is this nitrogen lone pair, okay, so we know that nitrogen is more basic than oxygen. That's why this nitrogen lone pair will grab this proton and it will generate this molecule. And if I am reacting this particular intermediate with my alcohol functional group, then this oxygen lone pair will attack at this carbon. This CO bond will form double bond here and this nitrogen will get neutralized. Okay, so this oxygen lone pairs attacking at this carbon, this bond is breaking and forming a double bond here and this nitrogen is getting neutralized. So you have formed ROCH2PH. So we just protected the alcohol with a benzyl ether group. Okay, so this is the main product. And what is the byproduct? This is the byproduct. So Cl3C, C double bond O, and we have NH2. Okay, so let me number them: A, B, C. So here it will be A, B, and C. So this is another way of protecting your alcohol functional group with a benzyl ether simply by using this particular reagent under acidic media. So this is something interesting you should know. Okay, let's talk about the treatyl protection group. So what it is? So this can be written as ROTR. And what is this TR group? So this can be written as ROCPH3. So treatyl group is basically CPH3. Okay, carbon attached to 3-phenyl ring. So this is what we call a treatyl group. Okay, so in a treatyl group, which can be written as TR, is nothing but CPH3. Now, important thing, a note about this reaction or about this particular protection strategy is that this is selective for 1 degree alcohols. Okay, so take a note that this particular strategy is very selective for 1 degree alcohols. Now let's talk about protection. So this is my alcohol group. If I react this with treatyl chloride, so what is treatyl group? Treatyl group is CPH3. So I can write CPH3Cl. Basically I removed or I substituted this treatyl group with CPH3, and this is what we call treatyl chloride. In presence of triethylamine as a base and DCM as a solvent, so this oxygen lone pair will attack at this carbon, Cl is going to leave, and you will form ROCPH3. In other words, RO treatyl group. And what about deprotection? To deprotect, you need a acidic environment. Okay, you need an acidic environment, and you will be able to generate your alcohol. And what is the byproduct? Byproduct is this very stable tertiary carbocation, which can be later attacked by any nucleophile present. And this can form this molecule. So this is all about treatyl protection group, which is very selective for 1 degree alcohol. Treatyl group is nothing but CPH3. To protect, you use treatyl chloride, and to deprotect, you use acidic environment. So this is about treatyl functional group. I mean treatyl protection strategy. Now let's talk about PMB. So PMB stands for para-methoxy benzyl protection. Okay. So let me talk about protection first. So this is my alcohol. If I use PMBCl, what is PMBCl? PMBCl is para-methoxy benzyl chloride. Okay. So this is my benzyl group. This is benzyl chloride. At para we have OMe, that is methoxy group. So this is what we call para-methoxy benzyl chloride. In presence of a base, this oxygen lone pairs will attack at this carbon, Cl is going to leave, and you have formed RO, CH2, a ring, and OMe. So this is what we call ROPMB. So to do para-methoxy benzyl chloride protection, you need to use this particular reaction, this particular reagent in presence of a base, and you will be able to generate ROPMB. So this is about the protection by using PMB. Also, one more variant can be made to do the same para-methoxy benzyl protection. You can use, so we have just discussed it. Under acidic environment. So we have already seen this just few slides before. So this NH will grab this proton, later this oxygen will attack at this center, this will migrate here, and this will get neutralized. So we have just discussed it. So you can use this reagent also to generate your para-methoxy benzyl protection. Now I want to deprotect it. I want to get back my alcohol group. So which reagent should I use? So there are total of 4 reagents you can use. Use any one of them and you will be able to convert your ROPMB back into ROH. You can use DDQ, which is a base, or you can use hydrogen palladium, okay, or you can use sodium in ammonia, or you can use CAN. What is CAN? CAN is ferric ammonium nitrate. So use any one of these and you will be able to deprotect your ROPMB back into ROH. So this is about protection and deprotection of alcohols using PMB, para-methoxy benzyl strategy. Okay, let's talk about MOM strategy. So suppose I have a alcohol and I'm reacting this with MOM chloride. So what is MOM? So the full form is methoxymethane. Methoxymethane. So the full form of MOM is methoxymethane, and we have taken a chloride version of it. So it is going to look like this one. So methoxymethane. Okay. So this oxygen lone pair can form double bond here and can remove Cl group. So the resonating structure will be this one. Now here comes the alcohol functional group. So this oxygen lone pair will attack at this carbon and will neutralize oxygen, and you will generate RO CH2O CH3, and this is what we call, this can be represented as RO MOM. Okay, so this group is represented as MOM. So this is about protection. If I want to deprotect and I want to get back my alcohol group, I have to use a Lewis acid. Lewis acid like this particular boron reagent, and you will be able to generate the alcohol functional group. So what is the deprotection mechanism? So we talked about protection mechanism. What is the deprotection mechanism? So this is my protected product. So this Lewis acid will chelate with this oxygen, okay, and it will form a carbocation here. Then this oxygen lone pair will form double bond here, and this whole group is going to leave. So you have now RO Lewis acid, any Lewis acid, any metal attached here. Here it will be boron, okay, and then this can be further hydrolyzed back into your deprotected product. And what is the byproduct? So this one is the byproduct. So during this process, the Br group is going to leave, which later come again, will attack at this carbon, will neutralize it, and will form the mom bromide. Okay, so this is a mom group and this is bromide. So this is about mom protection. Okay, now similar to mom, we have meme protection. What is the full form? Full form is methoxy ethoxy methane. So suppose I have this alcohol group and I am reacting this with meme chloride. Okay, so we have methoxy, so I am writing methoxy. We have ethoxy, so this is my ethoxy, and we have methyl chloride. So methoxy, ethoxy, methyl chloride. Okay, so the mechanism is same. This oxygen will eliminate Cl group, and later this oxygen lone pairs will attack at this carbon, neutralizing oxygen, and you will generate RO meme. So mechanism is same. Okay, the strategy is same like mom chloride. To deprotect, once again you have to use Lewis acid. The mechanism is going to be the same, and you will generate the alcohol functional group. So this is about the meme chloride or the meme protection. Okay, now let's talk about the RO-THP protection. So suppose I have this molecule. Okay, so this is what we call dihydropyrylyl ether. Okay, now this particular molecule under acidic medium, so this oxygen lone pair will form double bond here, and then this double bond will grab this proton. So we have generated this particular molecule. Now further the alcohol will come, and this oxygen lone pair will now attack at this carbon, neutralizing oxygen. So you have formed this molecule, and this is what we call the RO-THP. So this was dihydro because we have one double bond here, but now this is completely saturated, and this time this is same name, but this time it is tetrahydro. Okay, this time we have tetrahydro. Now this is what we call the RO-THP protection. So this RO is here, and this THP group is corresponding to this particular architect. Okay, now I want to get back my alcohol. Okay, I want to deprotect my ROTHP back into alcohol, so I have to use a acidic medium. You can use acid source like PPTS, or you can use Umberlist 15. This is a basically acidic resin, and you will be able to get back your alcohol functional group. So this is about ROTHP. This is how you protect. You have to use dihydropyranil ether in presence of acid and alcohol, and you will form ROTHP. And to deprotect, you have to use acidic medium. Okay, so this is all about the ether protection. Whatever we have discussed till now, basically we are converting alcohol into ether. So this is all about alkyl ether protection. Now let's move forward and talk about silyl protection strategy. But before we jump into that, there are two more things we need to know. Two more strategy we have to know. So first let's look at that and then move forward to silyl protection. Okay, now I'm going to talk about the acetyl protection. So we know acetyl group can be written as this particular moiety. So suppose I have a alcohol and I'm reacting it with acetyl chloride. So acetyl group is this one, and this is my chloride version. So this oxygen lone pair will attack here. Through conjugation, Cl is going to leave, and you have formed the protected alcohol called ROAC. And to deprotect, you can use acidic or strong basic condition, and you will get back the alcohol functional group. So this is about acetyl protection strategy. One more thing, it's called pivalate ester strategy. So we have alcohol, and if I react it with its chloride version, so this PIV group represent tertiary butyl carbonyl. Okay, so this PIV group is representing this much, and this is a chloride version. So this oxygen lone pair will attack. Through conjugation, Cl is going to leave, and you have generated RO C double bond O tertiary butyl. So this C double bond O tertiary butyl is what we call ROPIV. You have formed pivalate ester. So this is a ester bond, right? So that's why it is named as pivalate ester. And to get back your alcohol, you have to use, particularly here, you have to use metal hydride bond. And that can be like any metal hydride bond, like sodium borohydride, lithium aluminum hydride. You can use dibalH. So use any one of them to convert your ROPIV to back ROH. So you have to use metal hydride bond. So in all of this, the H minus is directly bonded to a metal, that is boron aluminum. So this is about the ROAC protection and deprotection. This is about pivalate protection and deprotection. So now let's talk about the silyl protection. Okay, so till now we have talked about the alkyl ether. Now let's talk about silyl ether. Okay, so this is my alcohol, and I'm reacting this with any silyl chloride. So mechanism is same. Use base, this oxygen lone pair will attack on silicon, chlorine is going to leave, and you will form silyl ether. Okay, and to get back your alcohol, you have to use F minus source. And why is that? Because the silicon fluorine bond is much stronger than silicon oxygen bond. So you need to know this, okay? Because silicon fluorine bond is much stronger than silicon oxygen bond, that's why silicon is here preferentially breaking the bond with oxygen and forming the byproduct is this one. Okay, so this is about silyl ether. So you protect your alcohol group with silyl ether by using silyl chloride. You use any F minus source and you will get back your ROH simply because silicon has much more affinity towards fluorine as compared to oxygen, and that's why it is breaking the silicon oxygen bond here and forming silicon fluorine bond here. Now what are the F minus source you can see? You can see like pyridine with hydrogen fluoride. You can use HBF4 minus. So this is my first reagent. You can use second one. You can react with HF, water, ACN mixture. You can use SiF4, indicium. So one thing you will be able to observe is that for deprotection, as I have said, you need to use fluoride source. So here fluorine is present, here fluorine is present, here fluorine is present, here fluorine is present. So you will be able to look for the fluorine atom present in your reagent, and you will be able to understand that yes, I have to remove or break this SiO bond and deprotect my alcohol group. So this is about silyl ether. Now let's talk about what are the different types of silyl ether protection we have. So we have many silyl ether protection group, but the widely used one are, we have RO-TMS. So TMS stands for trimethyl silyl group. So we have trimethyl group. Then we have ROTES. TES is basically triethyl here. So RO silicon triethyl group. Then we have ROTBS, or this can also be written as ROTBDMS. So TBDMS stands for tertiary butyl dimethyl. So we have silicon bonded to tertiary butyl. So we have tertiary butyl and a dimethyl group. Okay. Then we have ROBPS. So BPS stands for, so BP means biphenyl. So you have two phenyl ring and a tertiary butyl group. Then we have ROTDS. So this can be represented as RO silicon methyl methyl. Then we have this particular molecule here. Then we have RO TIPS chloride or TIPS corresponding silyl group. So TIPS basically means that triisopropyl. We have triisopropyl group. So this is isopropyl group, and we have three isopropyl groups. That's why it is named as RO triisopropyl silane. Okay, so these are the 6 silyl groups we have. We have ROTMS, trimethyl, triethyl, tert butyl dimethyl, we have BPS, TDS, and we have triisopropyl silane group. So we have seen the protection, use chloride version of it to protect, and to deprotect you have to use F minus source. Okay, so once again I'm discussing the protection. So you have alcohol. So suppose I'm taking TMSCl. You have to use the chloride version of that silyl group. So TMS stands for trimethylsilane. So we have trimethyl and silyl chloride. Okay, you have to use base. So this oxygen lone pair will attack at this silicon. Chloride ion is going to leave, and you have formed what we call the ROTMS, right? And to deprotect, you can use like F minus sources, and you will be able to generate ROH. Just to mention, in few of the examples you can also see H plus, or you can also see basic media to deprotect your TMS group. So you need to know that TMS can be deprotected and get back the alcohol group by using acid or base. So in general, 99% of the time you will see F minus source, but you need to keep this in back of your mind that silyl group can be deprotected under slight acidic or basic medium. And also to protect, I have used the chloride version. Okay, so you can keep any leaving group here. You can see TMS, OTF. Okay, it is possible. You can see TMS, OTS. Basically this oxygen is going to attack at silicon and chloride ion is going to leave. So all these are working as a leaving group. So you can see any one of these reagents, but the chemistry is same. This group is going to leave, oxygen is going to bond it to silicon. And depending upon what group you want to keep here, you can take the corresponding leaving group attached starting material. Okay, so this page is going to be very interesting. Okay, this is going to be very interesting because we are going to learn so many new things here. So we know we have ROTMS, that is nothing but 3-methyl group attached to silicon. We have ROTES, that is silicon attached to ethyl group. We have ROTBS or TBDMS, that is tertiary butyl dimethyl. Fine. We have ROBPS, which is 2 phenyls and 1 tertiary butyl. We have ROTDS, which is this corresponding molecule. We have RO tips, which is nothing but 3 isopropyl group. So what is the stability order? What is the stability order? So for example, I'm taking this one and this one. Let's compare these three and compare their stability. So you need to know more bulky, that will be more stable. Okay, more bulky, that will be more stable. More bulky, that will be more selective for 1 degree alcohol. Fine. For 1 degree, or you can say less hindered alcohol. And also more bulky, that means more stable, and if it is more stable, it will not cleave easily. So don't cleave first. So these are the three important things. More bulky, that will be more stable, that will not cleave first. So if you are doing deprotection, it will not cleave first because it is more bulky. I'm going to give you the example. Okay, and also if it is more bulky, it will be more selective for less hindered alcohol. That means 1 degree will be more reactive than 2 degree, and lastly the 3 degree, because 3 degree will be more hindered as compared to 1 degree. Now out of these three, OTMS, OTS and OTPS, what is the stability order? So it is very clear, right? This is more bulky as compared to this one. Here we have ethyl, here we have only methyl. So stability order is going to be, tips will be more stable than ethyl one, and lastly the methyl one, right? Okay, so this is the stability order. More bulky, more stable, and it will not cleave first, and it will be more selective for 1 degree alcohol. So remember these three things very clearly. It will help you in solving practice problems, which we are going to discuss in next video. Okay, so let me give you one example. So what is the product? I'm using just one equivalent of F minus source. Let's say I have TBAF, tetrabutyl ammonium fluoride. So we know we have only one F minus source. So out of these three, only one silyl group is going to deprotect and will generate OH. But which one of them? So TMS is 3-methyl group. Then we have TBS, which is nothing but people also call TBDMS, is this one. And we have TIPS as 3 isopropyl groups. So let me name this A, P and C. So which one is stable? Let's talk about the stability. More bulky, this is definitely more bulky than this one, then this is least bulky. So stability will be, more bulky is more stable, C, B, A. Okay, so which will not cleave first? Do not cleave first. So order is going to be the same because more stable will not cleave first. And which one is more stable? More bulky. So C, B, A. So clearly the cleavage order is going to be the reverse, A, B, C. So this is less stable, less bulky. So this is going to cleave first, and out of these three, in presence of only one F minus source, the product is going to be only TMS is going to deprotect and will generate OH. Rest will be intact. So you need to know this, as I mentioned. So you need to know all these silyl groups. Then only you can know which is more bulky, which is less bulky. And if you know the more bulky one, that will be more stable and that will be more reactive towards less hindered alcohol. 1 degree, then 2 degree, and lastly 3 degree. And more bulky will not cleave first. So this is what we applied here. And this is how we got the product. Out of these three, C is most bulky, so it will not cleave first. The least bulky will cleave first, and we simply deprotected our OH group and we got the product. Now suppose I have 2 F minus. Then this will get deprotected and this will intact because this is more bulky. Okay, so we have discussed in detail with mechanism the protection and deprotection of alcohol functional group. We have seen the alkyl ether protection, we have seen the silyl ether protection, and we tried to solve some problems also. And in next video we are going to discuss few more practice problems, and then things will get much clear. So this is it, and thank you for watching.